Hello students, I am Mansi Agarwal, ABES Engineering College, Ghaziabad. Today we will be discussing our next topic of data structure, that is binary search algorithm. Binary search is a searching algorithm for finding a target value within a sorted list. It works by repeatedly dividing the search interval in half. If the target value is less than the middle element, the search continues in the left half. And if the target value is greater than the middle element, then it continues in the right half. This process repeats until the target is found or the interval is empty. So the basic constraint of the binary search algorithm is that the elements in which we have to search the target must be sorted either in ascending order or in descending order. The second thing that we have to remember is that the binary search algorithm works on divide and conquer algorithm technique. So the target value is always searched at the middle index. And if the target value is less than the middle index, then the search continues in the left half, thereby ignoring the right half of the array and decreasing the size of the array in every iteration by half. Similarly, if the target value is found to be greater than the middle element, then it continues the searching process in the right half of the array, thereby ignoring the left half of the array. And the process is repeated until the target is found at the middle element or the effective array, that is the interval, becomes empty. To have a better understanding of binary sort algorithm, let us take an example where suppose we have 11 elements in the array and these elements are stored in sorted order, in ascending order. Suppose the elements that we have are 11, 22, 30, 40, 55, 60, 66, 77, 80, 88, and 99. With the index starting with 1 and ending at 11. Suppose the target value that we have to search is 40. So for executing the binary search algorithm, we first have to take two variables, namely beginning and end, that will always store the index representing the first index and the last index of the effective array. So as we know that in the first iteration, we have to search the element in the entire array. So the beginning will have the value 1 and the end will have the value 11. Now in every iteration, suppose if we are talking about the first iteration, we have to calculate the middle index of this effective array. And the middle index will be given by beginning plus end by 2. So here in the first iteration, the middle will be calculated as 1 plus 11 by 2. That will come out to be 6. Now in every iteration, there will be 3 cases. Whether we have found the target value at the middle position. So firstly, we have to check whether the value at middle position is equal to target or not. If we have found the value at the middle position, then the search will stop here and we will return the middle index. But in this case, as you can see, that the value of A mid here will be 60, which is not equal to the target value. So we will move on to the second case, wherein we can check whether the value of A mid is less than the target value, right? So if it is less than the target value, in this case, we will shift the beginning variable. But as you can see here, that a mid is 60, which is not less than target. So this case will also not be true for the first iteration. And the third case that we have to check is whether the value at a mid is greater than our target or not. Yes, as we can see that a mid is 60 and the target value which we are searching for is 40. So this condition is true. Right. So in this case, what we have to do is we have to reduce the array in such a way that the right half of the array will be ignored and the search process for the next iteration will remain in the left part of the array. So for this, what we will do is we will shift the end to mid minus 1, right? So the end, which was 11, will now become 6 minus 1, that will be 5, right? So now for the next iteration, the effective array will reduce to this. And this is pretty clear that we know that the elements are sorted and the middle element is 60. So definitely we are going to find the target value in the left portion of the array, right? So for the next iteration, that is iteration second, again we have to calculate the middle index with the same formula, beginning plus n by 2, but with the new values. Here, the value of beginning will remain the same, that is 1, but the value of end has been modified to 5, divided by 2, which will give us 3. Again, we have to check the 3 conditions, whether the element at index mid, that is index 3, is equal to target. No, because the element at index 3 now is 30. Then we have to check whether the element at a mid is less than target. Yes, it is less than target. So in this case, if a mid, which is 30, is less than the target value which we are looking for, which is 40, then what we have to do is we have to shift the beginning to mid plus 1, thereby ignoring the left half of the array and continuing the search in the right half of the array. So here the value of mid was 3. So 3 plus 1 will become 4. This is the new value of beginning for the next iteration. Right. Now, coming on to the next iteration, iteration number 3. Here again we have to calculate the mid index, which will now be calculated with the new values. That is 4 plus the value of end was 5 by 2. And now this will give us 4. Now you can see that the value stored at a mid is nothing but the target value that we were searching for, which is 40. Hence, the search is successful and we can here return the index of the middle target value. Let us now suppose that the element that we have to search is 35. Suppose the element that we have to search is 35. Now, as you can see that 35 is not present in the array. Let us just see that how this search will proceed. Now, in this case, you can see that again, beginning will store the value 1 and n will have the value 11. For the first iteration, the mid will be calculated in the similar way. That means it will be 1 plus 11 by 2. It will come out to be 6. And the middle value will be greater than the target. So n will be shifted to 5. Till this point, the search will be proceeded in the similar way. Then afterwards, again in the second iteration, mid will be calculated, which will come out to be 3. And the value of a mid is 30, which is less than the target. Again, the target is 35. So the beginning will be shifted to mid plus 1, that is equals to 4. Now, in the next iteration, in the iteration number 3, when we will calculate the middle value, that will come out to be 4 plus 5 by 2, which is equals to 4. Here we are not getting the target value at the fourth index, right? Because the value of the fourth index is 40. Now again, as we can see that a mid is greater than the target value that we are looking for. A mid is greater than the target value. So in this case, the n will be shifted to mid minus 1. And here, the n will become 4 minus 1, which is equals to 3. So at this point of time, you can see that beginning is holding a value 4, while end is holding a value 3, which shows us that the interval or the effective array in which we are looking for a target value has become empty. So this is a condition where we say that the search is unsuccessful. Let us now quickly see the algorithm. The algorithm, as you can see, has 3 parameters where A is the array, n is the number of elements, and target is the value that we have to search. As discussed earlier, beginning is equals to 1, which means the first index of the array, and end is equals to n, that is the last index of the array. Now, while beginning is less than equals to n, this is the condition till what we know that there is at least one element in the effective array. So, till the time beginning is less than equals to n, we have to calculate the middle index, which is equals to beginning plus n by 2. And then there will be 3 conditions. The first condition is where we have to check whether the element at the middle index is equals to target. If it is equals to target, then we have to return mid. This means the search is successful and we have to return. Otherwise, we have to iteratively check whether the value stored at middle index is less than target. If it is less than target, then we have to shift beginning to mid plus 1, thereby searching in the right half and ignoring the left half. Otherwise, if the value of a mid is less than the target value, we have to shift the end to mid minus 1, thereby ignoring the right half of the array. And if the search is unsuccessful, we will come out of this while loop when this condition of beginning is less than equals to end will be false, as it was shown earlier for the example 35. In this case, we have to return a minus 1, showing that the search is unsuccessful. So now we can go and see the implementation of this code. Let us start with including the header file, stdio.h. This is required in order to use the inbuilt functions printf and scanf. Now, void main, let us take an integer array and we need a variable position to get back the position of the successful or the unsuccessful search, and a variable val to store the value, the target value, and we need n to store the number of elements in the array. We can quickly ask the user to enter the number of elements. And then we can take this value inside n. Then taking n elements from the user, we need to write a loop, and the loop index will start with 0 and it will go till n minus 1. Inside this, we can ask user to enter the element with its number. We can say that please enter the I plus 1th element. And we can input this value inside the array with scanf %d ampersand a of I. After this, we have to input the target value from the user. We can ask the user to enter the target value or the value to be searched. And we have already taken a variable val to store this value. Now, with this value, we have to call our user defined function. Maybe we can name it as binary search. And as we have already discussed, the number of parameters for this function will be 3, including array, and the number of elements in the array, and the value that we have to search. So first of all, we know that if the position that we will get, if it is equals to -1, then that means the search was unsuccessful. So we can here write that the search is unsuccessful. And else we will get the position, we will get the index of the target value. So in this case, we can write that the value %d is found at %d position. Right? In this case, the value is stored in val and the position is holding the index. So we can write position +1 to give the position, the actual position with respect to the user. So now quickly implement the algorithm for the binary search. And in order to implement this, we have to make a user-defined function with the name binary search, wherein we have 3 parameters: array, the number of elements, and the value that we have to search. Now, In this particular function, we have to first take a variable beginning that will be initialized with 0, and we have to take end that will initially store the last index, which is n minus 1. And we also need a variable mid that will be calculated in every iteration. Now, as you must remember, we have to check whether the value of beginning is less than or equal to end or not. Only in this case, we can check whether the target is found at the middle position or not, right? And otherwise, if this condition is false, then we will return minus 1. So we can here write return minus 1. So inside the while loop, first we have to calculate the value of mid, which is given by beginning plus end by 2. And we have to check the three conditions, whether the value at a mid is equals to target or not, which is stored in V. If it is so, then we have to simply return the middle index that is given by mid. If it is not so, then we have to see whether the value stored at the middle position is greater than the target value or not. If the value stored at the middle position is greater than the target value, then we have to ignore the right half. So in this case, end will store the value mid minus 1. And otherwise, if the value stored at the middle index is less than the target value, and we have to shift the beginning so that it will store the value mid plus 1. Right, so this is how the algorithm will be implemented. Let us try to execute this algorithm. Let us suppose the number of elements are 5 and the elements can be 2, then 4, 6, 8, and 9. And suppose we are searching for a value 8. So you can see that we have got the output that the value 8 is found at 4th position. Now, coming back to the algorithm, binary search algorithm can also be implemented recursively. In order to implement the binary search algorithm in a recursive way, we need to have 4 parameters where we have array, the lower index, the higher index, and the search key. Again, there will be 2 base conditions. The first condition is supposed to be the low index should be less than equals to high. Definitely, if the value of low is going greater than high, that means the search is unsuccessful. In this case, we will return minus 1. Otherwise, we will calculate the value of low by taking the floor value of low plus high by 2. We will see whether the value stored at the middle index is equals to search key or not. If it is so, then we will return mid. This is another base condition. And if it is not so, then we have to keep on searching the element in the 2 halves, whether in the left half or in the right half, depending upon the value of a mid. If the search key is less than a mid, then in this case, the binary search will be processed from low to mid minus 1. And if the value of search key is greater than a mid, binary search will be performed from A mid plus 1 to A of high. Now, in order to compute the time complexity of the binary search algorithm, we know that the complexity is divided into three ways, wherein we have to discuss the best case, average case, and the worst case of any algorithm. So, in order to discuss the best case, we can see that if we find the target value at the middle index in the first iteration itself, that will be said as the best case of the algorithm. And in this case, there will be only constant time as the number of iterations will not be dependent upon n. So we can say that the best case complexity of the binary search algorithm is omega 1. What about the worst case or the average case? Suppose we say that the time taken in order to search the element in an array of size n is Tn. So we can say that this Tn is equals to Tn by 2 plus C, as we can say that in every iteration, the size of the array is reduced by half and there is some constant steps that we have to follow. Like in this case, we have to check the value of low and high. Then we have to compute mid. Then we have to check whether the value is found at the middle position or not. Then there will be the recursive calls. In the similar way, we have to follow these steps in the iterative approach as well. And then the values of beginning and end are shifted in a way that the number of elements becomes n by 2. So again, in the next iteration, we can say that this is equals to T of n upon 2 square plus C, that is 2 of C. And next iteration, this will become n upon 2 to the power 3 plus adding up the constant will become 3 of C. In the same way, we can say that suppose after k iterations, the value of Tn becomes T of n upon 2 raised to the power k plus k dot C, wherein we can suppose that n upon 2 raised to the power k will give us 1 as there is only one element left in the effective array. So we can say that n upon 2 raised to the power k is equals to 1. So n is equals to 2 raised to the power k and taking log on both the sides, we got the value k is equals to log of n. Putting this value in this final equation that we got, T of n can be computed as T1, where n upon 2 raised to the power k is equals to 1, plus log of n dot c, which can again be written as c plus log of n dot c. Ignoring the constant terms, we will get log of n. So we can say that the complexity of the binary search algorithm is log of n. So the average case complexity can be represented with the theta notation, giving theta log of n. The best case complexity is omega 1. The worst case complexity is big O log n. Now, if we talk about the space complexities, we can see that in both algorithms, whether we are talking about the iterative algorithm, in the iterative algorithm, we have taken beginning, end, and mid as the variables, which makes it a constant space complexity. And also in the recursive algorithm, we have taken low, high, and mid. But in case of iterative approach, the complexity remains O1, while in the recursive approach, the complexity becomes O log of n. This is because of the call stack that is created in order to implement the recursive algorithms. So as we know that in the worst case, there are log of n calls. So for every call, there will be one element added to the call stack. And so the recursive approach will give us O of log n complexity. The references taken for this video includes data structures using C and C++ by Tenenbaum, Langsam, and Augustine, fundamentals of data structures by Horowitz and Sahani, data structures by Shorms, and data structures using C by Thareja. Thank you.